So in our warm-up here, we're asked to evaluate the following without a calculator. And you'll notice it's 45, 30, and then we'll talk about pi over 3, but that's actually 60 degrees. So I gave you a little hint on referring to the special right triangles. What we're going to do today is basically get you to a point where you feel really comfortable with these types of problems. And we're going to base them off of the coordinate plane. So what I'm going to do here is just draw a quick little sketch for this. And what we want to look at is the angle that's given, whether it's in degrees or radians, is considered my reference angle. Right? And we spent last Monday, Tuesday, drawing in a reference angle of 45 degrees. So if I look at this, then this has to be a 45, 45, 90 triangle. So I can take the values from the special right triangle and place them around each spot. So I would have the side length of 1, 1, and square root 2. So once we have that set up, we are hoping that you understand, okay, let's see. We've got cosecant. Well, I think cosecant is the reciprocal of sine, right? Now, I know that sine is equal to opposite over hypotenuse from SOHCAHTOA. So what we're looking for is the reciprocal of that, which is hypotenuse over opposite. So I'm going to follow my reference angle. The reference angle is always formed at the origin, and remember, it was from the initial side to the terminal side, and we're at 45 degrees. So the opposite is 1, the hypotenuse is square root 2. So then my answer would be 1 over square root 2. However, if we were to look at a calculus textbook or a pre-calculus textbook, they actually take this answer and they do something called rationalizing the denominator, which we did in geometry. So hopefully you guys remember doing that. Square root of 2 cannot be on the bottom, so we're going to multiply by the square root of 2 on the bottom. And I get the square root of 2 times the square root of 2, which is the square root of 4. But instead of writing the square root of 4, square root of 4 turns into 2. So there is the final answer for the cosecant of 45 degrees. All right, now we're going to do the same thing with cotangent at 30, but the 30 degrees is a different reference angle. We're looking at this one here. So do you have to redraw this? Not technically, especially if you have that written out, but I'm a visual learner, and if you don't have this in your head already memorized, or you don't have it on your paper, then I would draw this out again. So my reference angle is 30 degrees, so I'm going to go from the 0 line up 30 degrees. And again, these are just estimates. It doesn't have to be a very detailed, perfect drawing, because we know that that's 30 degrees. And it's always going to be a right triangle, so then 30, 60, 90. And across from the 30 is 1, across from the 90 is 2, and across from the 60 is square root 3. And that's going to be true every single time. All right, so now we're going to go ahead and identify what is cotangent. Well, cotangent is the reciprocal of tangent, and if tangent was TOA, opposite over adjacent, then cotangent is adjacent over opposite. So I'm going to go and look at my reference angle. Square root of 3 is the adjacent, 1 is the opposite. So then my answer is the adjacent over the opposite. And the square root of 3 is over 1. It would probably just be written as square root of 3 because dividing by 1 doesn't change the outcome. Okay. And then the last one, we've got secant of pi over 3. So now I got to think, well, pi over 3. Well, think of this. Pi is the same as 180 degrees. So 180 divided by 3 is 60 degrees. So that's how I deal with my reference angle. If I drew this a little more accurately, 60 degrees would be kind of a taller triangle than the 30 would. So it might look closer to this. Here's 60, 30. Now notice it's still 1, 2, square root 3. Across from the 30 is 1, across from the 90 is 2, and always across from the 60 is square root 3. And then I want to think about secant. Well, secant is the reciprocal of cosine. So if cosine is the ca in SOHCAHTOA, that was adjacent over hypotenuse. So if I flip that upside down, hypotenuse over adjacent, then I just have to identify, here's my adjacent, here's my hypotenuse. And then we can identify, well, the hypotenuse was 2 and the adjacent was 1. So we would call this 2 over 1 or just 2. Okay, so this might be a lot depending on where you're at. If you've memorized the special right triangles and you know SOHCAHTOA, this is pretty quick. Eventually, we're going to get to the point where we can do all of this without showing any work. And that's something called the unit circle. That's what we were gearing up to for this week. Okay, really quick, I just want to quick point out Wednesday, the expectations for Wednesday, and I'll show you right here. Week 6, you should have gone to the Wednesday folder and opened it, and it says log into Delta Math, find the Wednesday 1-13 assignment, and then watch the videos and take notes. Those notes are what we're going to continue on with today. And I'm going to review a little bit, but not all of it. So half of you did not watch, actually only 15 people watched the videos. And of those 15, some of you only watched half of it. So I'm really nervous that we're not doing the expectations that are set forth, and that's going to set us behind, and you're going to struggle. So if you did not watch those videos, you're going to have to go back and watch them at some point, hopefully in the next day. All right, we are going to do 4.3 day 2, evaluate trig functions and angles in the coordinate plane. Okay, so you don't have to write the learning target, but title it 4.3 day 2. And I said this before, but this is the stuff that you are going to have mastered when you move into calculus. And we're spending a couple extra days on it to give you time to have it completely mastered. All right, so this is basically the same thing that was written on the other page. I'm going to do a quick review. This is from the video that Ms. Dwyer had that you were supposed to watch yesterday. And hopefully you can make a strong connection to this. Okay, we're looking at evaluating the 6 trig functions on the coordinate plane. So we know what sine is, we know what cosine is, SOHCAHTOA. And because we know those 3, we know their reciprocals. And that's what we're going to be basing it off of. But instead of giving you numbers or angles, we're going to do this with a generic setting to help you recognize the pattern. Okay, so let's start with this. We can do these as we go. We're going to do sine, cosine, and tangent. And once we have those, then we automatically know the other 3 because of the reciprocals. So what I'm going to do is I'm going to pick any random point, but to be safe, we're going to plug this, or we're going to say this point right here is at the spot x, comma, y. Okay. Now, when I say x, we're referring to your movement along the x-axis. So we know that this length is in the positive direction. call that x. And then if I go up, this height right here is y, and it forms a right triangle from the origin to the spot where we ended, and that is going to be called r for our radius. And then because this theta is the same for all of these ratios, theta just represents the angle measure that's formed between the x-axis and the terminal side. So that's my reference angle. So let's look at, well, what is sine, cosine, and tangent as ratios? And if you want to, I'm using SOHCAHTOA. And I'll try to color coordinate this, but sine is opposite. So where's my opposite? It's right here. Opposite of theta. And then adjacent to theta is x, and the hypotenuse is r. All right, so if I can color coordinate this, opposite was the y value. Hypotenuse is just the r value. And that's what's going to give us the ratio for any sine function. It's your y value over whatever your radius would be. And we could, if we know the location, which you'll see on the next example, if we know x and y, we can use Pythagorean theorem to find r. And eventually, once we get to this, r is actually going to be 1, which makes these ratios really much faster and friendlier. So we'll share that in a little bit. Cosine is the c, which is the adjacent over hypotenuse. And the adjacent was the x value. And the hypotenuse is the r. And then tangent was TOA. So that's the opposite over the adjacent. And the opposite was the y value. And the adjacent is the x. So now that we know SOHCAHTOA, sine, cosine, and tangent, we automatically know their reciprocals. So I purposely lined these up where the reciprocal of sine is cosecant, which is hypotenuse over opposite. And then the adjacent over hypotenuse, that was cosine, so its reciprocal is hypotenuse over adjacent. And if tangent is opposite over adjacent, then cotangent is adjacent over opposite. You don't have to write this. Some people like it. So that is what we are kind of expecting you know going into today. And we're going to build off of that as we move along. So I'll give you a second to finish writing this. So if an angle is in standard position and its terminal side passes through the point -4, -6. Well, when I see this, right away I'm thinking -4 is the x-coordinate and y is -6. So if you've memorized, which I don't recommend doing that, but if you've memorized what sine is, sine was y over r, all you need to figure out is the radius, and you got sine and then cosine and tangent. You can do this very quickly. But since this is one of the first times we're going to do it, what we want to do is we want to go ahead and kind of graph this as if it was just a point. So if I start at the origin and I go -4, right? Well, -4 takes the x value and brings it to the left 4 units. And then the -6 would bring us down 6 units. And that location then, here's the point right here. That's where we would end up. Well, that already forms the right triangle from the origin to that point. And we now know that this angle is my reference angle. That's what theta is right here. So all of these angles are based off of the reference angle of theta because it's from the terminal side to the closest x-axis. And then we also know that here's my adjacent, here's my opposite. The only thing we don't know is the radius. Right? So that's what we got to do a little bit of work for, is we need to figure out how long is the radius r, which would be the hypotenuse. So if I call this side the hypotenuse, I'm going to make reference to it as r. Well, if I take -6 and square it, and -4 and square it, that's the Pythagorean theorem. Notice something really quick before we get our answer. When I square negatives, they turn into positives, right? And the square root of a positive will always be a positive. So your radius will always be a positive length. And then when I add this together, I get 52. And I don't know if that can be reduced. I'm going to just, yeah, it can. I'm going to leave this for right now. Even though it could be reduced, this could be turned into, I'll just show it to you quick, but it could be 4 times 13 is 52. And then the square root of 4 is 2. So, yeah, you know what? No, let's take it. Let's take this answer instead of this one. Because I think that's the way they would do it if you were given a delta math problem. So I had to do some work to figure out what the radius is. And our answers aren't going to be pretty, which is fine. But now we're able to go ahead and calculate sine, cosine, and tangent. I'm going to do a little pre-work here. So I'm thinking SOHCAHTOA right now for these 3 pieces. So sine is opposite over hypotenuse, cosine is adjacent over hypotenuse, and tangent is opposite over adjacent. Right? Now, we've also learned that based off of theta, well, wait a minute, the adjacent is the x value. Right? So instead of saying adjacent, I could call that x. So anywhere I have adjacent is officially the x. And then the opposite, that's how far I went up or down. In this case, it's the y value. So the opposite is y. And then the hypotenuse, instead of calling it a hypotenuse, we called it r. So we know the ratios for sine, cosine, and tangent. I don't care how you learn it. I personally like to stick with SOHCAHTOA, but I know that they refer to as y over r as sine, x over r is cosine, and tangent is y over x. There's a reason why, and I'll show you that coming up. But now all we do is just plug in our numbers just like we had before. So sine is opposite, which is the y value. Now notice, why would it be beneficial to know y and x and r? Because you technically wouldn't need a graph like this then if you just did Pythagorean theorem between these 2 points and found your r. You could still get the same answer. So if I did -6 over r, which was 2 square roots of 13, I'm going to reduce this later because we don't like that square root of 13 on the bottom. But I'm going to wait until I do that, and you'll see why. And then x over r is -4 over 2 square roots of 13. And the y value, that was -6 over the x value, which is -4. Now, this is the only one I would reduce right now. So -6 over -4, well, that's going to reduce out to 3/2. And then since tangent and cotangent are reciprocals, we know cotangent very quickly. Okay. We could actually reduce this one too. See how the -4 and -2 would reduce? I might do that reduction right now. See if I can give myself a little bit more room. Oh, shoot, these are connected. I can't. But if I divide this 2 and this -4, I'm left with a -2 over square root of 13. So then if I flip that, secant is 13 over -2. I like to just put the negative out in front. You could put the negative out in front. You could put the negative up here with the 13. Or you can put it down here. It really doesn't matter. But notice, by not reducing the radical here, we're in correct form, where we have the correct form here. And then same thing, this 2 and this 6 would divide out, so I'm left with -3 over square root of 13. And then sine and cosecant are reciprocals, so we're going to flip that. So the only thing that would be left to do, I'm happy with this answer because the radical's in the numerator. Same thing here. And this one doesn't have radicals, so I have 4 answers that I'm really happy with. These two, we have to reduce the radical or rationalize it. So we just got to get rid of that square root of 13 in the bottom. So we times top and bottom. I should have given myself more room. I hate pushing this over, but I get negative square root of 13 over 13, and that is the answer to sine. And then you would do the same thing with cosine. To get rid of the square root of 13, we got to multiply top and bottom by the square root of 13, and that leaves the bottom just as 13, and then the top is -2 square roots of 13. Okay, so you should have seen a video like this, or a problem like this in the video from Wednesday. You saw it again here. And this works no matter where I put the point in the circle. If I put it over here, you can still get an x and a y. If I put it over here, you can still get an x and a y. If I put it over here in quadrant 2, you can get an x and a y. The only parts that get us in trouble is what happens when a point is on one of the lines, the x or the y axis. Those are special, and it results in something that we're going to talk about with the x and y's coming up. Okay, so quadrantal angles. Miss Dwyer talked about this a little bit in the video. I want to really hit home how we approach these so you can understand what's going on. And there's one thing that we have to make an assumption for here, and I'll share that with you as you draw this out. Okay. So if we have quadrantal angles, and those are angles that have their locations on the terminal sides on the x and y axis, that would be something like right here. This is in between the two quadrants, so we call it a quadrantal angle. Here's another one, here's another one, and here's another one. So we have a small problem when we have pieces like this, because don't draw, I'm going to erase this part right here, but when we had a point here, we were able to go over x and up y, and we were able to find the radius r, right? Because that formed a triangle. But when I have a point that's on one of these quadrantal angles, I end up not having a x or a y, or one of these x or y's is 0. So the problem with that is we have to come up with another way to kind of solve this. And here's what we're going to kind of show you is, first off, what are the values at each point, right? We talked about this. This was 0 degrees or 0 radians. Actually, I'll do radians in a different color. Let's just deal with degrees, right? And we saw this one was 180. Mr. Dwyer went all over this before. Half of 180 was 90. So every quarter turn was a 90 degree, which made this 270 degrees. And if I come back, we could also call this 360. So those are the 4, if you count 360 and 0 being different, but they're not, they're coterminal. But those are the 4 quadrantal angles. Well, what would that look like in radians, right? So we have 0 radians. If I take pi, which we talked about 180 was pi, if I cut that in half, that was pi over 2. So every quarter turn was pi over 2. So this was 2 pi over 2, 3 pi over 2, and then this would be 4 pi over 2, which ends up being 2 pi. So notice 90 or pi over 2's, that's going to kind of tell me where I'm located. So let's look at the sine at pi over 2. Now, what was sine before? Sine was opposite. I'm going to jump back really quick. Sine was opposite over hypotenuse, or y over r. So what if our radius is 1? And that's kind of the key here. We're going to learn more about that coming up. But if the radius was 1, that means the sine is just the y value. And cosine was x over y. So if the radius was 1, the cosine is just x. And that's kind of how we're going to evaluate these. All right, so sine end up being y over r. Well, if I'm at this point, notice I have a location. So what if I say the radius right here is 1? Maybe I'll do that in a different color. Right? Because if I spun this around, if I spun the radius around, I would get a circle all with the radius of 1. Well, what if I moved up here? That still has a radius of 1. And this one still has a radius of 1. Every single dot is 1 unit away from the origin, whatever that happens to be. So if this is 1, let's think about the location of these points. This dot right here is at the spot go over 1, up 0. And this point right here is at the spot go over 0, up 1. This dot is at the spot go over -1, up 0. And then this spot is go over 0, down 1. So notice, those locations still have an xy pairing. Right? We know what x is, we know what y is. And if sine of 90 is the y value over the radius. Well, the y value is 1, the radius is 1. So sine of 90 is 1. And again, it might take you a little bit of time to get used to this. But what would cosine of 90 be? Well, cosine was x over r. Well, we know what x is. At 90 degrees, we're at the spot over 0 up 1. So x is 0 when r is 1. So cosine of 90 degrees is 0. And then here's the tricky spot. What is tangent? Right, well, tangent was y over x. And we know what y is. We know what x is. So y was 1. X is 0. But we can't divide by 0. Which means this is undefined. All right, well now, if I know what tangent is y over x. Well, cotangent is x over y. It's the reciprocal of that. And I already know what they are. It's 0 over 1. Well, 0 divided by anything is 0. Okay? So notice all 4 of these problems were based off of the same reference angle. 90 degrees, 90 degrees, 90 degrees. It's all based off of this point right here. And then I decided to just throw one random one at you to see how we would do on that. So what is tangent of negative pi over 2? So negative refers to us going clockwise around the circle instead of counterclockwise. And we're going to go negative pi over 2, which, remember, that's the same as negative 90 degrees. So where would that be? That would put us right at this point, which another way to say this is what would the tangent of 270 be? Because I could go this way instead of 90 degrees this way or 270 this way. Those are coterminal angles. And then all we would do is have to figure out, all right, tangent. Well, what is tangent? Tangent is y over x. And if I'm at this point right here, that means I started at the origin, I went over 0, down 1. So the x is 0 and the y is negative 1. And now we know what y and x is. So negative 1 over 0. And then we actually end up with that same divide by 0, which we can't do. So we are undefined at that value. Okay, I'd like you to try some of these quickly. So on the next page, I've got problems just like this, but you have to pick out the reference angle. And I will tell you they are all quadrantal angles. So it's either going to be located at 0, 90, 180, 270, or back to 0, which is 360, or we could make reference to their radians. So let's take maybe a couple minutes to do these 4 or 6 problems. See how far you can get. And then I'll go over it and show you how I would approach this problem So let's go over these problems here, and I'll just show you how I would approach this. If I notice that all of the angles are based off of the quadrantal angles, what I would do then is I would go ahead and kind of draw a picture like this. And if it's for degrees, let's do these two with degrees first, and then I'll change these to radians, and you'll see how we would approach those. So if I'm thinking cosecant of 90 degrees, well, I'm thinking, well, where is 90? 90 degrees, we know where that is. So what would that be? If the radius was always 1, then this point would be go over 0, up 1. Well, that tells me exactly what x and y are. So then I have to think about, okay, cosecant. Well, cosecant is the reciprocal of sine. And if sine was y over r, then cosecant is r over y, which means the radius is 1, and then the y value is 1. And then technically you could leave your answer like that, or you could just call it 1. So that's how I do the first one. Then I'd think cotangent. All right, well, cotangent is the reciprocal of tangent, and if tangent was y over x, then cotangent is x over y. So I got to think, where is 270? 270 is right here, and I go over 0, down 1. And that's my x and my y. So then we know exactly where we're at. 0 over negative 1. And 0 divided by anything is still 0. So those are the ones that dealt with the degrees, but what about radians? Well, the only thing that's changing is how we think of those. So I'm going to go every quarter of the circle is a pi over 2. So this would be 1 pi over 2, 2 pi over 2, which we just write as pi. This would be 3 pi over 2. And this would be 4 pi over 2, or just 2 pi. So where is 3 pi over 2? That's all the way around the circle right here. We know what its x and y are already. So then I just got to think, okay, well, what is secant? Well, secant is the reciprocal of cosine. And if cosine is x over r, then secant is r over x, and the radius is 1. And in this case, my x value is 0. And I can never divide by 0, so I just call that undefined. Okay. Well, then we've got some other trickier ones. Negative pi over 2. The negative just refers to us going the other direction. So a negative pi over 2 is the same as going to negative 90. And it's sine, so I know that sine is y over r. So if I go negative 90, we know what the y is. The radius is always 1. So I end up with negative 1 over 1, or that reduces down to just negative 1. Then I decided to trick you guys and see if you understood what we meant when we say radians. So what is 3 pi? Well, 3 pi is really 2 pi plus another pi, right? 2 pi gets me all the way around the circle once, so then I just have to go 1 more pi, and that puts me right here at just basically pi, or 180 degrees. Well, what's this location? This is go over 1, up 0, and I went over 1 to the left, so it's negative. So that's my x and y. And tangent is the ratio of y over x, which is 0 over negative 1, or just 0. And if you think of negative 3 pi, well, I think of negative 3 pi as going once around the circle, but in the opposite direction. So we're going clockwise because it's negative. So that's once around the circle. And then another negative pi, which puts me right back to where I was at 180. And secant is the reciprocal of cosine. We did that over here, so it's r over x. We know the radius is 1, and my x value at this point is negative 1. Okay? So notice how we were not able to draw a right triangle. Those are any of these 4 locations, and that's where you have to use the relationships we just talked about. We are going to get a lot of practice with this. So if you're not comfortable with it right now, that's okay. Let me show you really quick. Ms. Dwyer talked about this, so you should already have notes in it. I'm going to do a quick summary. I'm not going to go over this in great detail. I'm going to show you a quick little shortcut that might help. But let's just look at, what if I have a random point in each quadrant? So let's call this quadrant 1, quadrant 2, quadrant 3, and quadrant 4. A lot of times I use Roman numerals to mark those, but so what if I have a point right here? What do we know about all the trig values? Well, it's based off of your x and y's. Right? So let's think of this. If my x's are positive and my y's are positive, we know that the radius will always be positive. So any point in here is a positive. Actually, I want to use this as a different color. Okay, so notice x is positive, y is positive. Anything in the first quadrant, x and y are both positive. And if x and y are both positive, that means all trig functions in quadrant 1 are positive. Okay? I'm going to underline that word all, and you'll see why in a second. Well, what happens then if I shift over to this point? If I have a point right here, I'd have to go negative x, but the y value is still positive. And our radius will always be positive because of the Pythagorean theorem. So what do we know about our points here? Anything that involves an x or the adjacent side will be negative. So what is positive here? This is another way to think of it, negative, positive. So what we have then is anything that involves the adjacent side, because remember, this is the angle that we're thinking of, that's theta. Anything that has the x or the adjacent would be negative. So that means that the positive signs are the ones that just involve y and r. And that is sine and its reciprocal. Those are the only ones that are positive. The negative values, the ones that have negative answers, are cosine, its reciprocal, tangent, and its reciprocal. Okay? And it's really all based off of your x and y values. That tells you what you know about which ones are positive and which ones are negative. Okay? Well, look at down here. What if the y value goes down here we still have a negative x because we're going over and down, and my radius is always positive, but the y value becomes negative here. So now anything that has both x and y combined, I would have like negative x over negative y. Well, that's a positive. So anything that has both x's and y's, which is tangent and its reciprocal, so tangent will be positive because it's opposite over adjacent, and that's a negative over a negative. So therefore, its reciprocal will be positive. And then, since all the other trig functions they involve the radius, that means one either x over r or y over r, those are all going to be negative. So that means that sine and its reciprocal and cosine and its reciprocal would all end up having negative values. Okay, last one. So what happens if I'm in quadrant 4? Oops, I forgot to do this for quadrant 3. What do we know about any point in quadrant 3? Well, my x was negative and my y was negative because I go over to the left and down. So any of these points would be negative, negative, and that's kind of going to help us remember how tangent and cotangent are the only positives. So what if I'm in this point right here at quadrant 4? Well, any point in quadrant 4 is over to the right, so your x is positive, and then down, so your y is negative. Well, what that means is these values, if it has a y in it, it's going to end up being a negative value. So we're thinking which of our trig functions that we learned before has a negative in it. So I'm thinking we'll deal with the negative ones first. The negative ones, sine is y over r, so that's negative over a positive. So that means that its reciprocal is also, that's weird, that looks weird. Its reciprocal is also negative. Cotangent involves the x value and the radius, so those are always going to be positive. I think cosine, I think I might have said that wrong. Cosine and its reciprocal. And then that leaves tangent. Tangent is y over x. So that would be a negative over a positive, or if we flip it around, positive over negative, but either way, their signs would be flipped. Okay, so we now know which values are positive in what quadrants. And if you just stick to what's positive, then the other ones have to be negative. So that's kind of how I think of it, is sine, tangent, cotangent. And some students, well, yeah. All right, so I don't want you to write the following. I just want to show you. And we got two problems that basically are using these results. And I'll show you how my brain works with that. And Ms. Dwyer kind of showed a different way to do this, but so don't write this, we're going to go pretty quick, but it says which quadrant does theta lie in based off of the following. So when we read this, it's asking me, when is tangent negative? All right, so tangent is less than 0, so that would be negative. And then here, when is cosine positive? Well, I'm going to go right back to my chart, and I want to figure out when is tangent negative, and when is cosine positive? If you have this chart, okay, tangent is negative here and here in quadrant 2 and 4. And when is cosine positive? Well, cosine is positive in quadrant 1 and quadrant 4. So the spot where they're both matched is quadrant 4. Okay? Now, there's another way to think of this, and it's kind of think of it as your own. Here's quadrant 1, 2, 3, 4. And this is the way that I would do it, because I don't have that chart memorized. But what do I know about tangent? Tangent is TOA, opposite over adjacent. So if this is true, then the opposite either has to be negative. In that case, that would put us over here and down. That's where the opposite angle would be negative and the adjacent would be positive. So tangent is negative here. But we could flip it around, right? I could go over to the left, which is negative, and up, which is positive. So that's the adjacent would be negative and opposite would be positive. But I know tangent is negative here. So from this statement, I know I'm either in quadrant 2 or quadrant 4. And then I'm going to look at when is cosine positive. Well, cosine is adjacent over hypotenuse. And we know the hypotenuse is always positive, right? So that means the adjacent, which is always the side on the x value, so we could have cosine being positive here, or cosine is positive down here. And where's the overlap? The overlap is in quadrant 4. That's where both of these, tangent is negative and cosine is positive. There are many different ways to solve this. If you were to watch the help video in Delta Math, it might explain it a little differently, which is fine. I'm going to skip this one. It's basically the same thing. I want to get to these problems. So we're probably going to be able to do a couple of these. Let's do 1 and 2 for sure. This is the ultimate goal right here. Can you do these problems without a calculator? And we are going to spend a lot of time on this. And you're going to see there is a shortcut eventually. So cosecant, I know that's the reciprocal of sine, but I first want to draw the reference angle, or I want to draw the angle 240. So I know 240 is 60 degrees past 180. So 240 minus 180 is 60 degrees, and that's my reference angle. So when I'm drawing that, I'm going to draw 180, and I'm going to go 60 degrees past that. I'm going to put a 60 right here. And then I've got 30, 60, 90. And across from the 30 was 1, but notice I went to the left, so that's negative, and I went down. So then across from the 30 is 1, across from the 90 is 2, and across from the 60 is square root 3. But notice the location. I'm in quadrant 3, so I go to the left. So x is negative and y is negative. Now, you have a couple of ways to do this. What is cosecant? Cosecant is r over y. Well, we know what r is. R is 2. And we know what y is. Y is square root 3. So you could write your answer as 2 over negative square root 3, and then simplify that. Or you could think, wait a minute, sine is opposite over hypotenuse. So you could also do this as hypotenuse over opposite. There's two ways to think of it. I'm going to go back and forth on those because I personally like this way, but I can see when this is beneficial. So regardless, it's 2 over the square root of 3, but we don't like that square root of 3 in the bottom. I'm going to rationalize it. And there's the final answer. Okay, let's look at this last one, and we won't get to these two, which is fine. Let's do 11 pi over 6. So here's the way my brain works. 11 pi over 6. That means pi over 6 is 30 degrees. I'm going to go 11 of them. If I went 12, notice this. What if it was 12 pi over 6? Isn't that the same as 2 pi? So I am 1 pi over 6 less than all the way around the circle, which is how I'm going to draw this triangle. I'm going to go all the way around except for 1 pi over 6. Okay? So the blue angle, 11 pi over 6, gets me all the way to here. Here's my terminal side. But then my reference angle is the same as actually doing pi over 6. Now, what do we mean by that? Well, pi over 6 is the same as 30 degrees. So this little angle right here is 30. I'm going to make that a little bigger. So I know that pi over 6 is 30, so this is a 30, 60, 90 triangle. 1, 2, square root 3. Using my special right triangles, and then across from the 1, notice that's going down, so it's the negative 1. And then I just have to figure out what secant is. Well, secant is r over x. We know what the radius is. We know what x is. So the overall answer is r over x. But then I don't like this as a square root in the denominator. We get 2 square roots of 3 over 3. And like I said, we're just getting to the point where this stuff is becoming routine. Eventually, it will become much, much easier. Okay. All right, so our homework tonight is 4.3 day 2, Delta Math. Submit a screenshot. Remember, conferences are next week, Thursday. I called a good amount of your parents last night and just told them what you were missing and what needs to be done. So get that stuff in, improve your grade, and we should be good to go. All right, have a great day. We'll see you tomorrow. I'll be available in my office hours if you need help.